So there's going to be a lot of introductory stuff here. But so your saliva has a base in it. You can use that to just swallow a bunch of spit to neutralize stomach acid, but also antacids exist. Tums or off-brand Tums. GERD is a condition of chronic heartburn. So not just when you've eaten an entire extra Mosbestos stuffed crust Little Caesars pizza. Sometimes it doesn't even take that much most of the time. But if you have this condition all the time, that's GERD. I don't remember what that stands for. I have a vague idea. But acids and bases are important to our health and really balance a lot of things in the human body. And acid-base chemistry in general is central to much of biochemistry and molecular biology. Amino acids are all, I believe, are all amphoteric, so they're both an acid and a base. We'll talk about that. Your DNA also contains bases. So it's a very, very important subject. Acids, some of their general properties, they're sour taste. They have a sour taste. Don't taste any of the acids in the lab. But if you want to taste an acid, you can try vinegar. But you probably don't have to taste it. Also Sour Patch Kids. They also dissolve many metals, and they'll turn blue litmus paper red. And they'll neutralize bases. So some of these, things like hydrochloric acid, sulfuric acid, nitric acid, acetic acid, which I mentioned, citric acid, carbonic acid, hydrofluoric acid, which is like the scariest acid to me. It dissolves glass, which is wonderful. And then phosphoric acid, which is used as a fertilizer. Also in a lot of buffers. Ooh, buffers. We'll talk about buffers. Not today. Bases have a bitter taste, so they're not sweet, they're bitter. There are a lot of bases. Bases are why coffee is bitter, actually. Caffeine is a base, very bitter base. They have a slippery feel. They'll turn red litmus paper blue, and they will neutralize acids. They're also present in a lot of poisons. So an evolutionary explanation for why they're bitter is because they're involved in a lot of these poisons. So if you taste a base, your body's like, no, 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 don't eat that. Sodium hydroxide can be used in petroleum processing, soap, plastic manufacturing. Sodium hydroxide is also lye. Is that potassium hydroxide? Might be either or. Potassium hydroxide or sodium hydroxide are also present in Drano, used to break up clogs and drains. They're like almost entirely, they're like concentrated sodium hydroxide. Sodium bicarbonate, baking soda. That's also what one of the components of something like Tums as an antacid. So if you have baking soda but you don't have Tums, you can just take a spoonful of baking soda. And things like sodium carbonate and ammonia. So which of these is a property not associated with an acid? C, yeah. Hank Green had a whole TikTok where he talks about how you can taste protons, because that's what you're tasting when you taste, or when acids are sour. Acids are sour because they have protons, and you're tasting those protons, which is kind of cool. Going to go over a couple definitions of acids and bases. The Arrhenius definition is entirely based upon what ions, or specifically the ions of H plus and OH minus, being delivered to a aqueous solution. So Arrhenius definition is specific to water. If it produces H plus ions, then it's an acid. If it produces OH minus ions, then it's a base. So hydrochloric acid is an acid because it produces H plus ions, and it's a strong acid, so it ionizes completely in water. Before you add it to water, though, it is a covalent compound. It is ionized by the water. H plus ions are very reactive, so If you see H plus written out, it's usually just to abbreviate the idea. There's never going to be a lone H plus ion in a solution. It is going to be attacked by something, or it will attack something else to form other species, particularly hydronium, or this will be like an H plus with a number of waters surrounding it. So H plus and H3O plus are used interchangeably, and they're just meaning an H plus ion in solution. Sodium hydroxide is a base because it produces OH minus ions. It is an ionic compound, and it dissociates into its component ions. So HCl, hydrochloric acid, is a covalent compound. So there's a covalent bond between the hydrogen and the chlorine, and it is ionized when it's added to solution. The sodium hydroxide is ionic, so they're already ions, and they are just dissociated by the water. Acids and bases then can combine and neutralize each other, right? Because if we add H plus to OH minus, we get back water. So that definition is fine for most bases, most acids, and only when you're talking about them in aqueous solutions. A more broad definition is the Bronsted-Lowry definition. And it's focused, instead of on the ions that are being added to the solution, is focused entirely on protons being donated or protons being accepted. So the movement of protons is what determines a Bronsted-Lowry acid or base. So acids are proton donors, and bases are proton acceptors. And I guess I should mention a proton here, H plus, is just a proton, because hydrogen only has one electron. If you take away that one electron, it also only has one proton, unless it's an isotope like deuterium or tritium. So by the Bronsted-Lowry definition and the Arrhenius definition, hydrochloric acid is still an acid because it's donating a proton to water. It's also adding a proton to the water. Right, so it classifies under both definitions. It's kind of like a, well, we'll get to some that are not the same under both, but it's like a circle is a square, or a circle is a square. A square is a rectangle, but a rectangle is not necessarily a square. All right, so square has to be the same length on all four sides. Rectangle does not, but it could be. The Bronsted-Lowry definition is also nice because it's more descriptive of what's happening in the solution. Instead of this proton being just sort of ambiguously given out into the water, it has to go somewhere. Right? It has to be donated to an acceptor. One of the compounds that doesn't apply or doesn't fit into the Arrhenius definition is ammonia. So ammonia doesn't have any OH minus ions. It creates them indirectly when you add it to water. So it's not an Arrhenius base, but it is a Bronsted-Lowry base. So in this reaction, we see, right, we have ammonia and we have water. One of those protons is donated from the water to the ammonia, and it becomes ammonium, and the water becomes OH minus. So that's the indirectly adding OH minus to the solution. And then acids and bases will always occur together because, or under the Bronsted-Lowry definition at least, because to be a donor, it has to donate it to something. To be an acceptor, it has to get that proton from somewhere. They don't just come out of nowhere. So here we have the hydrochloric acid donates that proton to water, and that water becomes H3O plus, and the hydrochloric acid becomes chloride. Some substances are amphoteric, which I mentioned before, which means that they can act as an acid or a base. So So for example, if we reverse this Bronsted-Lowry reaction, and now we write it as NH3 plus H2O comes OH minus plus NH4 plus. All right, water here is donating a proton now in the reverse reaction. We could also write this as H2O H2O plus something like HCl. So here we have, this is a proton donor, but with hydrochloric acid now it can become H3O plus Cl minus. So now water here is a proton acceptor. So it has to, from the same form, be able to both donate a proton or accept a proton to be amphoteric. So it's not so the ammonia here is not amphoteric because we flipped this reaction. We'll talk about what those are. Those are conjugate acids or conjugate bases. But it's that the fact that H2O can either donate or accept is what makes it amphoteric. In any acid-base reaction, you're going to have conjugates. So conjugates are, it's kind of like the word conjoined. A conjugate acid is a base to which a proton has been added. And a conjugate base is any acid from which a proton has been removed. So this means that conjugate acids, conjugate bases, are always going to be products. Right? Something has to have been done to it to make it a conjugate acid or a conjugate base. For example, here, ammonia is a base. If we add a proton to it, now that becomes a conjugate acid. So it's a base to which a proton has been added. Because now, if we take that and we flip it around, that proton could be donated to something else, making that an acid. And then for water, right, if we take water and we remove one of those protons, then that acid becomes a conjugate base. And then because in a Bronsted-Lowry acid or base, there's always a swap of protons that's always being donated from one to the other. You're always going to have an acid, a base, and a conjugate base, and a conjugate acid. So you'll always have all four in a reaction. All right, so we're going to identify the conjugate acid, or the acid and the base, and the conjugate acid and the conjugate base. So let me zoom. There we go. So which of these is the conjugate acid, or which one's the acid? Yeah, H2O is going to be our acid. Because, and this is all about tracking protons, right? So water here has 2 protons, and in the products, it's OH minus, meaning it's lost that proton. So it was donated somewhere. So what's our conjugate base? Yeah, OH minus. And because we've identified the acid, we've identified the conjugate base, what does our base then have to be in this? It's going to be the C5H5N, which I think is like pyridine. Yeah, so this is going to be our base because it's accepting the proton from the water. And then our conjugate acid is going to be the protonated form on the other side. So the base and the reactants will always be the conjugate acid in the products. The acid in the reactants will always be the conjugate base in the products. I think that's what that is. All right, how about in B then? Where's our, let me, here, so we don't have to worry about naming things. A, B, C, or D, which is our acid? One vote for A. Does anybody want to vote for anything else? Nope. Uncontested. Yeah, that's our acid. So that makes our conjugate base nitrate. And then our base has to be H2O, then the conjugate acid. So far, this should all be review. Cool. So which of these is not a conjugate acid-base pair? Any votes for A? No. For B? Bunch of votes for B. Any votes for C? No. Yeah. B is the only one where the number of hydrogens doesn't change. H2SO4, H2SO3, change in oxygens. But a conjugate acid-base pair has to do with a change in hydrogens. All right, acid strength. This is where we start breaking away from and going deeper than Chem 20 level stuff. The strength of an electrolyte depends on the extent of its dissociation into ions in solution. So to put this into equilibrium terms, it's how big that K value is for the equilibrium, right? How many more ions does it produce in solution than the electrolyte itself? If it produces a lot of ions, it's going to have a really high K value, meaning that it completely dissociates. So it's dependent on that equilibrium between acid, or the conjugate base, and the acid, or the conjugate acid and the base. So strong acids completely ionize in solution. They have essentially an infinite Ka, right? They completely dissociate. It's all products, no reactants. A weak acid only partially ionizes, and that's where most of the math has to be done. Because if it only partially ionizes, that means it's got a really small K for the equilibrium, and we get to calculate the concentrations at equilibrium. Here's a list, 6 important strong acids to memorize. Hydrochloric acid, hydrobromic acid, hydroiodic acid, and then nitric acid, perchloric acid, and sulfuric acid. We can describe we can describe acids based on the number of protons that they have. So monoprotic, meaning 1, diprotic, meaning 2, triprotic, meaning 3. And most of the time, the strength of an acid changes depending on which ionization state it's at. So like something like sulfuric acid, for its first ionization, will be a strong acid, but for its second ionization, could be a weak acid. We'll talk more about those later. So for strong acids, all of these strong acids, this list, ionize completely. And for sulfuric acid, specifically the first ionization state. So going from H2SO4 to H plus HSO4 minus. And in the case of these strong acids, which are also strong electrolytes, actually use a single arrow for your reaction because it's all going from reactants to products. There's really no reactant left over. Right? So K is essentially infinite. And strong acids are very nice. Strong bases are also very nice because you don't have to do an equilibrium calculation. You can look at a strong acid and say, if I have 1 molar HCl, that's going to produce 1 molar of H+ ions in solution and 1 molar of Cl- ions in solution. Weak acids, on the other hand, don't ionize very much. They'll produce some amount of ions, H+ ions in solution, but compared to strong acids especially, where they completely ionize, it's usually a very small amount that the weak acids actually ionize. So there's a very significant portion of it that exists in the solution as HF, or the hydrofluoric acid. So for weak acids, this is why you need to know which ones are weak and strong acids, a 1 molar hydrofluoric acid solution is going to produce much less than 1 molar H3O plus ions. Right? Very little hydronium is going to be made, which is why you get to calculate it. So with acids and bases, when you take the acid, I should just use this here, HA, right, reacts with water, it ionizes, forms hydronium, and a conjugate base. The strength of that conjugate base, as a base, is sort of inversely proportional to its strength as an acid. So in this case, we're talking about weak acids. So if HA is a weak acid, then A- is a strong base. And that's because the acid strength depends on the attraction between the conjugate base and the hydrogen ion. So in these weak acids, the anion, is very strongly attracted to the hydronium, or the hydrogen. So that means that if you take that, oh, sorry, I was circling the strong acid. I was talking about weak acids. So that means if you take this A- ion and it doesn't have a proton, it's going to want to pick up a proton. And it'll grab one from wherever it can. Strong base. Strong acids don't care at all about their protons. They just give them up. They're terrible parents. Just let them go. So the stronger the acid, the weaker the conjugate base. And then the reverse is also true. Weaker the acid, the stronger the conjugate base. All right back into equilibrium. So for acids specifically, we have an acid ionization constant, that's Ka. Later we'll have a base ionization constant, Kb. The Ka represents the equilibrium state for an acid in solution. So it's a way that we can quantify the strength of a weak acid. Right? This isn't going to matter for strong acids because there's going to be none of the acid left in solution. It's going to be completely ionized. Again, K is going to be essentially infinity. But for these weak acids, we're going to spend a lot of time with Ka and equilibrium expressions for those acids. And the smaller the Ka means less ionization, hence weaker acid. So here's a bunch of these acids. We've got some inorganic acids at the top, things like chlorous acid. Chlorous acid has a pKa, or a Ka of 1.1 times 10 to the negative 2, which Kas are not super convenient to work with unless you have to do calculations. I like pKas. We haven't talked about pH yet, but you've probably heard of pH. Some ridiculous people sell like alkaline water, and they're like, ooh, it's pH 8. And I'm like, that's going to give you chemical burns. it won't give you chemical burns. I doubt it's even pH 8. But that pH is related to the pKa. So if we get lower than a pH of 1.9, or if we get to a pH of 1.96, that actually means that half of this is ionized. And then if you go below that, more is ionized after that. If you're higher than, no, backwards. More of it is ionized if the pH is higher than the pKa. Yeah, we'll look into the math of this. There's some other acids on here. So these are inorganic acids, meaning that they don't contain carbon. These ones down here are organic acids, or most of these are organic acids, meaning that they contain carbon. And we will talk a little bit in this class about organic chemistry later on. And acid is also a functional group in organic chemistry. So acetic acid is an organic acid. Alrighty. So consider these three generic weak acids, HA, HB, and HC. And they represent the ionization of each acid at room temperature. So these are at equilibrium. So which of these is the largest Ka? Any votes for A? No. B? One vote for B, one vote for A. Any votes for C? Anybody who has no idea? That's fine too. Okay, so the Ka is going to be equal to the concentration of the H plus and the conjugate base over the concentration of HA. So in these diagrams, and maybe I should have explained this first too, the little white balls, those are the protons. So here we have 1 proton. Here we have 4 protons. Here we have 2 protons. And then there should be, yeah, so like this one is a conjugate bases. But we can just focus on the protons. So if our Ka is higher, larger number, does that mean we're going to have more or fewer protons? More protons, right? So which one is our, has the highest Ka? B. Yeah. So higher Ka means more ionization, means more protons in the solution. So if we consider these two acids, we have hydrofluoric acid and hypochlorous acid. Which of these acids is stronger? A. Does anybody disagree with A? Yeah, it's A. Right, so smaller negative exponent means it's a higher concentration because it's a larger number. All right, so talked about water being amphoteric, meaning it can act as either an acid or a base. Water auto-ionizes. So in any solution of water, pure water, you're going to have water reacting with water to form some hydronium and some hydroxide. And it's a very teeny tiny amount, times 10 to the 7, -7 of each, actually. So, well, here's water acting as an acid. Showed you something like this before, right? So that goes from H2O to OH minus, donates a proton. We can have water acting as a base. So here, again, H2O, but it's accepting now this proton from hydrochloric acid to become hydronium. So you can also have water reacting with water. Dang it, I should have prepped that meme. I have a meme for this one. I'll find it real quick. So water reacts with water, and one of them gains a proton, is a base. The other one donates a proton, it's the acid. It's the chemistry memes. No, well, that's a good one. There's another one. I think it's also with Thanos. No, well, that's also. what happens when you dissolve something. It's gone, reduced to ions. I think the actual line's ashes. Where is it? Ah, yes, there it is. Right, so water reacts with itself. I used the water to destroy the water. Sorry. Oh, you can't, that's right, I forgot. I've done this one before. It's Thanos, but you can't even really tell. Stupid projector. So the water destroys itself. Use the water to destroy the water. It auto-ionizes. It doesn't do so a lot. There's not a lot of that. So it happens too at a predictable rate. So a lot of this stuff, a lot of the equilibrium stuff, is all about just like statistics. It's like how many water-water interactions are there? Some small percentage of those end up in a reaction, just like we talked about with rates. All right, correct orientation and enough energy. So we can write this Kw, right? So this is equilibrium constant for water auto-ionizing. And because on the left side, it's just liquid water, we leave liquids and solids out of the equilibrium expression. We just get the concentration of H plus times the concentration of OH minus. And then there's Kw as a measured thing. And Kw equals 1 times 10 to the negative 14. Right, so that's the equilibrium constant for autoionization of water. So if we do the math, then we can calculate that the concentration of H3O plus is going to be equal to the concentration of OH minus in pure water. There's nothing else involved. So very, very small amount, but it does. And then it's this balance between H3O plus and OH minus is how we define acid concentration. So pH is all based on how many protons are in the solution. We'll talk about pOH too, and that's how many hydroxide ions are in solution. And it's just shifting this balance one way or the other. They always will add up to or multiply to get 1 times 10 to the 14. It's just how much of it is protons, how much of it is OH minus. All right, so neutral is balanced. So for our acidic solutions, just like I was saying, they contain an acid which creates additional H3O plus ions. And the ion product constant still applies, so the concentration of OH minus decreases. So for our water, if the concentration of H3O plus increases, that means that the OH minus concentration has to decrease, so that Kw still equals 1 times 10 to the negative 14. In a basic solution, then we contain a base that creates additional OH minus ions, and then OH minus increases, so H3O plus decreases. It's just which side of the teeter-totter are you pushing down on? So we've got H3O plus concentrations for 3 solutions. Which of these solutions was acidic? Is it A? Votes for A. 1 vote for A. Is it B? Nobody says B. How about C? 2 votes for C. So if an acidic solution has a higher concentration of H3O plus, which of these has the highest concentration of H3O plus? It's A. Yeah, I know. I hate negative exponents. I think they're just inherently confusing. But yeah, so that means that 10 to the negative 3 is actually the highest concentration, so this would be acidic. 10 to the negative 7 is actually, let me write this, this is acidic. 10 to the negative 7 is neutral. And 10 to the minus 9 would be basic. So opposite side of things now. Right, we're now looking at, oh, no, sorry, this is a different question. Calculate the H3O plus concentration for each solution, and then we'll determine if it's acidic, basic, or neutral. So for these problems, we can use the equilibrium expression for water, for autoionization of water, where Kw equals concentration of H3O plus times the concentration of OH minus. Right? So that's just an equilibrium expression specific to water, no reactants, because our only reactant is liquid water. And Kw is something that you should memorize. It comes up a lot. So Kw is 1 times 10 to the negative 14. So that's going to equal our H3O plus times the concentration of OH minus, which we're given, 1.5 times 10 to the negative 2. So really all we have to do is divide 1 times 10 to the 14 by 1.5 times 10 to the negative 2. So this is just like any of the equilibrium questions that we went over, where you have K and you have all of the concentrations of everything else, and you're calculating the equilibrium concentration of the one missing thing, right? So it's just a little simpler for water. 1e to the negative 14 divided by 1.5 e to the negative 2. So this concentration of H3O plus is 6.67 times 10 to the negative 13 molar. So is that acidic, basic, or neutral? Basic, yeah. So the concentration of, well, I guess it looks a little confusing the way it's written here, but it's part of the expression. Right? Our OH minus concentration is larger than our H3O plus concentration. This is going to be basic. Just a basic solution. All right, so for this next one, same process. Right? We are still using the autoionization of water, and so we can just take that and plug in new numbers. So 1 times 10 to the negative 14 equals H3O plus concentration and, well, our OH minus concentration, which is 1.0 times 10 to the negative 7. So 1e to the 14 divided by 1 times 10 to the negative 7 means that H3O plus is equal to 1 times 10 to the negative 7. So acidic, basic, or neutral? Neutral, right? Concentration of our acid is the same as the base. And then rinse and repeat for the third one. Actually, before I even go through the calculation, can you guess what this one's going to be? Basic or acidic? Acidic, right? Because this is a very small concentration of OH minus. So that means we're going to have a large concentration, relatively speaking, of H3O plus. 1 times 10 to the negative 14, H3O plus. Oh, so much writing. So 1e to the negative 14 divided by 8.2 e to the negative 10. So H3O plus is 1.22 times 10 to the negative 5. So larger H3O plus concentration than OH minus. So that means this is going to be acidic. Any questions? All equilibrium stuff. All right, a better way to talk about acids and bases, in my opinion, is pH. Simplifies things a lot, cuts out a lot of numbers. The pH is the negative log of H3O+. So a solution with a H3O+ concentration of 5.3 times 10 to the negative 8 molar would be the negative log of 5.3 times 10 to the negative 8. And also, if you have this calculator, you have to press the log button twice. You have to use log log, which is log base 10, and not ln log, which is natural base log. If you're getting wrong numbers for everything, despite thinking that you're doing it all correctly, that might be your mistake. So this is going to be 7.2, we got 2 sig figs, 2.8. No, see, look, I'm so used to doing that. So I'll have a pH of 7.28. Logs are interesting too because as the note says here at the bottom, only the decimal places of the log number are significant. Because all that this 7 is telling us, the 7 is indicating the times 10 to the negative 8. The rest of these numbers tell us if it's, or determine if it's 5.3 or 5.4. That's the significance. Logs are a little weird. Oh, also, while we're talking about calculators, if your calculator has a scientific mode, it's probably going to be useful for this section. So it'll take all of your numbers and automatically put them in scientific notation. So you don't have to count zeros. All right, so the pH scale is based on this negative log of the hydrogen concentration, H3O+ concentration. So anything with a pH less than 7 is going to be acidic. Anything with a pH equal to 7 will be neutral, and then greater than 7 will be basic. And you can kind of prove this to yourself too, right? If you want to look at the concentrations, you say, okay, pH of, well, we haven't talked about yet how to calculate it going the other way. So a pH of 3, though, you would do 10 raised to the negative 3 would equal 1 times 10 to the negative 3 molar. All right, relatively large concentration of H3O+. So that would be acidic. You can see that on the bottom here, the pOH scale is exactly the opposite of the pH scale. So here we have a pH of 4. That's a pOH of 10. We'll talk more about pOH, though. Oh, and yeah, and you can get actually negative pH values for concentrated acids. Really high concentrations. All right, so we're going to calculate the pH of each solution and then indicate if it's acidic or basic. So definitely type this into your calculators. Make sure you get the same number that I do. So this is just the negative log, 9.5 times 10 to the negative 9. So I got 8.02. Is that acidic or basic? Basic. About the pH of those ridiculous waters. OH minus concentration. So here we're given the OH minus concentration, but we want pH. We can actually calculate this 2 ways. We haven't talked about one of them. So let's do the one that we have done. And we'll use that Kw equals H3O+ times OH minus. You might remember the other way. So this is going to be 1 times 10 to the negative 14. So it's H3O plus times 7.1 times 10 to the negative 3. So it's going to be 1.40845 times 10 to the negative 12. And then we want the negative log of that number. So this is going to be 11.2 sig figs, 85. Wish I had a better way to move that to the top of the screen. I guess I could do this. It's just the top of the next slide. Anybody not get 11.85? This is somewhere, so for pH, POH, these calculations, anytime that logs are involved, exponents, that's where rounding errors can result in very, very large errors for your final answers. So as much as possible, try and keep every number in your calculator or write out several digits to retype into your calculator. Okay. Good. So if we want to do the opposite now and calculate the H3O plus concentration for a solution with a pH of 8.37, the opposite function is 10 to the negative 8.37. So actually, let me 10 to the negative pH equals H3O plus concentration. That's the formula. So 10 raised to the negative 8.37 is going to be 4.2 2 sig figs. Yeah, so 4.3 times 10 to the negative 9 molar H3O plus. This should again be review, hopefully. All right. So for POH, now we do everything that we did for OH, but we're using concentrations of hydroxide instead of hydronium. All the same functions. So if you want to calculate POH, it's just the negative log of the OH minus concentration. We're transforming the data, we're not converting the data. So technically POH is not a unit. It's just telling us that it's the converted concentration. So now we can look at the bottom of this, our POH scale. So for high values of POH, like 14, that's going to be acidic. And for low values of POH, that's going to be basic. It's the exact opposite of pH. And you can think of this also as P is just means negative log. So if we want the pKa, that's the negative log of the Ka, or generically px would be the negative log of x. So pH, negative log of H concentration. POH, negative log of OH. Okay. So this is the other way to convert between pH and POH. And it just comes from, again, the autoionization equilibrium constant for water, equilibrium expression. So Kw equals H3O plus times OH minus. And then all we do is take the negative log of both sides. So negative log Kw equals the negative log of H3O plus. Actually, this is in parentheses, times the OH minus. And then as a property of logs, we can take that negative log and now say the negative log of H3O plus plus the negative log of the OH minus concentration. And again, this is still negative log Kw. And Kw is just a value, so we can plug that in. Actually, I'll do that right here. So this is going to be 1 times 10 to the negative 14. And then the negative log of H3O plus is just pH, plus the negative log of OH minus concentration is just POH. And the negative log of 1 times 10 to the negative 14 is just 14. So if you want to convert between pH and POH, you don't have to go to concentration first. Right? If you plug in pH, we can solve this for POH and say 14 minus pH equals POH, or 14 minus POH equals pH. I think it's a neat little derivation. It's nice that taking the negative log of everything just gives you pH and POH. And it's a little more convenient to type 14 minus some number, which isn't going to be a huge number. It's not going to involve large exponents. Right? A little easier to calculate, at least in my opinion. Anybody need more time on a slide? I'm not going to ask you to derive this probably. Yes, the circle of life, or pH. And actually, it's more of a square. The square of pH. It's not as catchy. So this is just how we can calculate all of these things. There's, from pH, we can calculate POH, or we could calculate H3O plus. And, oh yeah, let me write these in actually. So 14 minus pH, that'll give us POH. If we do 10 raised to the negative pH, that'll give us H3O plus concentration. And we can do the reverse of those too. So negative log of H3O plus will give us pH. And 14 minus POH gives us pH back. Actually, I think I made this too small. Aha. Cool. So we can also go from POH down to OH minus. So 10 to the negative POH. Or back the other way, negative log of OH minus. And then we can calculate between these two as well. That's going to be 1 times 10 to the negative 14 divided by OH minus. Or this way is 1 times 10 negative 14 divided by H3O plus. the square of pH. So there are a lot of ways that you could calculate your way around the square. Most things can be done in a single step, but if you have to travel from one corner of the square to the other, then you have to either go through the pH, POH route, or you have to go through the H3O plus, OH minus route. Both are valid. This is one of those things, helpful graphics that you can like memorize, but like cram memorize, and then before you do anything else on the exam, flip to the back page and scribble it onto the back real fast. Definitely did that. Definitely done that before. Is everybody done with this? Oh, just splattered coffee all over my laptop. Okay. So, as the pH of a solution increases or gets higher, what happens to the acidity of the solution? As pH increases? Yeah, acidity decreases. So pH, remember, if we have a pH of 1, that's acidic. If it's increasing to 14, that's basic. They may be whole numbers now, but they still feel backwards. Even now, they still feel backwards to me, right? You think, oh, the concentration or the acidity is increasing. You think, oh, pH should increase, but it does the opposite. It decreases. Oh, I guess they're at time. Let's see. All right, we can stop there. Yeah.